Hello, I'm Ed Hoffman, the Director of the NASA Academy for Program Project and Engineering Leadership, and I welcome you to Masters with Masters. This is our second in a series that explores the science, engineering, and management of our programs and projects. Very fortunate, very excited to have two of NASA's best, Dennis McCarthy and John Mather. And as way of introduction, I'll just briefly indicate that John Mather is the Senior Astrophysicist at the Goddard Space Flight Center and the Senior Project Specialist for the James Webb Space Telescope. His research centers on infrared astronomy and cosmology. John earned his doctorate from the University of California at Berkeley and his doctoral thesis on measurements of the cosmic microwave background radiation that led directly to his work for about 20 years at NASA. He's also the recipient of numerous awards, including the Nobel Prize in Physics, which he shared with George Smoot in 2006, and the NASA Distinguished Service Medal in 2007. He's a co-author of The Very First Light, a book which talks about the history of COBE and the background to that. And so please welcome John Mather. And it's also my pleasure to welcome Dennis McCarthy. I've known Dennis for many years as well. During his career at NASA, Dennis served as Deputy Project Manager for the Cosmic Background Explorer. He also served as the Deputy Project Manager for the Hubble Space Telescope Servicing Mission and the Deputy Associate Director of Flight Projects for the Hubble Space Telescope. Recently, Dennis has been the Chief Technology Officer for the Hawk Institute for Space Sciences, and it's a pleasure to welcome Dennis McCarthy. So as a way of getting started, looking at some of the critical experiences that lead to a career, I was going to start first with John. Your dissertation research in terms of the cosmic background radiation, you started doing research in a balloon project, which you talk about, it was a failure, and that had a great impact on what happened later with COBE. Can you get us started maybe there?
Yeah, sure. Well, it was 1970. I was looking for a thesis project. We had just landed on the moon the year before. So people started saying, well, we've measured also the cosmic background radiation from the Big Bang, but the measurements are all pretty bad. It's time to start graduate students trying to measure this thing. So I started in with a thesis advisor, and first we made a ground-based measurement, and that was pretty hard because the air gets in the way. But we began to learn the techniques and technology for it. Then the next step was to go fly a balloon payload. So hanging an instrument on a string thousands of feet below a high-altitude balloon is as close as you could get to space without actually going into space. So basically we built ourselves a small satellite hanging on a string to try and measure this cosmic background radiation. So we did pioneer in that measurement the concept for the instrument that would eventually fly on the Cosmic Background Explorer. And it was not my original concept. My thesis advisor thought it up. But we all saw that at the time it would have been better if it could have been done in space. Now, the payload did actually fail to work right the first time that it was flown for 3 different reasons, all having to do with the fact that it was really cold up there. And so we had just gotten tired of testing. Testing is tiresome, tedious, boring, and essential. And so the conclusion that I drew from that was, if you do not test it, it will not work. There's no such thing as risk that it will not work. It's a certainty that it will not work. So that is a discovery that really felt in my bones. And when it came time to work with a real flight project, it was something that was real clear to me. So I never believe real risk assessments, and I never believe that an analysis can prove that things are really okay. So that's the sort of life-changing experience of that. I also made a decision at that time that I would never work on this cosmic background radiation again because it was too difficult. But NASA did change my mind a few months after I finished school because they asked for scientific proposals for new satellites. And so that's what became the Cosmic Background Explorer. So you never know what's going to happen.
Right, the impact of the early studies having that impact. So Dennis, before getting on to COBE, what were some of the experiences that prepared you to be the Deputy Project Manager and to deal with the management issues of COBE?
Well, I think when you asked me that question recently, I think what I did was I worked on various programs as an engineer. from mechanical engineering to systems engineering. And in that process, I used to watch project managers. Something told me I ought to watch them. And there were all kinds. Some people empowered everybody around them. Some project managers decided to do it all by themselves. And some would remove obstacles all along the way for people on their project. And some would just listen. People would come in their office and listen. And if you integrate all those different types of project managers, I think that's what I learned, just to watch them before I went and did project management on COBE.
You have, John, in your book, which is The Very First Light, there was, the whole book is like an adventure story, mystery that plays out. There's one section that particularly got my attention where you talk about scientists versus engineers. And being someone who's been involved in science, engineering, and management, can you talk a little bit about that whole notion of dealing with scientists and engineers on a complex management issue?
Well, let me just say that scientists and engineers have to work closely together, but we're really different. The scientists are likely to say, as I do, well, if it's not impossible, then let's do it. And the engineer has to say, well, I heard you, but I don't know how to do that. How are we going to do this? So quite a lot of my work with the engineering teams was to say, well, okay, this is what we need to do. Nobody knows how to do this. Are you sure, John, that you really have to do it that way? How about if we try something else? So it's a very creative interaction that we had to have throughout the project, because we were pushing the state of the art far beyond what anyone had ever tried to do before. This was the first project for Goddard that would involve serious cryogenics in space. We had our instruments to be cooled down to liquid helium temperature, only 1.5 degrees above absolute zero. It's not something any of us were familiar with. The scientists on the team had done some of it, but we have to admit that we're not capable of understanding what it takes to make that whole thing work in outer space. So there's a natural tension and a natural cooperation that has to occur. Now, I was blessed with good relations with engineering teams, and I could walk into any office of any engineer and have a chat about what the problem was and what maybe relief we might be able to give on that problem so it could be actually finished. So there was a lot of wonderful give and take that made the project great pleasure, also a great challenge, because there were plenty of things that seemed impossible all along the way, and some of them were. We just had to back off.
And Dennis, I guess you bring that management layer, and I guess scientists and engineers both agree that they didn't like, I shouldn't say you, but management. How do you deal with the management aspects of a science and engineering project?
I think the first thing was to communicate with the scientists all the time. In fact, I can tell you that John and I would have lunch once a week in my office with the door shut, just talking about this program and different aspects of the technical issues. The other thing is we were assured that we had written down what it is that John and the scientists wanted. So once we knew what the requirements were, instead of just this vague, it was a lot clearer to the engineering team what we had to do. But I think the key was to communicate, and as John said, we actually worked together all the time, engineers and scientists. I mean, John Mather and Mike Hauser and George Smoot would roam the halls and talk to their team, and it was a very good relationship that it worked every single day. Now, the only thing was, if one of them decided they wanted to change something, my initial answer was no. No first, and then we'll see what it is we could do with respect to the schedule and the budget. But we would work everything out every single day by communicating. And I think we got to understand the different languages between scientists and engineers.
Yeah, so you get the sense, or at least I get the sense, that the science, the engineering, the management was, I guess, respected enough that the folks knew what it was doing. I mean, did you do anything up front at the beginning of, this, I guess, 15, 20-year mission to get the team to understand what we needed to do together, or is it just the people you had that led to this kind of success?
I can give you an opinion, is the fact that an in-house program at NASA is very difficult because it's the best effort. NASA sometimes takes some of the best engineers on the in-house program and puts them on a high priority other program, and it's very difficult to control the budget or the schedule on an in-house program. And the reason that COBE was done in the end was because of the Challenger accident. It became more of a skunk works, and the system then dedicated itself to, we have to get this done.
Okay.
But a normal in-house program is difficult because it just goes on as a level of effort.
Oh, I wanted to add also that it was pretty difficult in this case to do what Dennis wanted us to do, which was to write down the requirements. Because we were pushing so far beyond what had been done that scientists could not imagine the requirements we had to answer. They needed to know what to build, and we didn't know what to build. So this is a time of great tension and uncertainty in the creative process.
It takes patience.
It takes a lot of patience. A lot of engineers were pretty annoyed with the scientists for a while because we couldn't tell them what we needed. And they were kind of expecting that we were smarter than we were. Of course, scientists like to think that they're smart, but there really is a territory where nobody's ever been before. And we have to sort of work together to explore that territory.
And the other thing on COBE, when it came to the cryogenics, we had a 100% failure rate of everything we tested in a doer along the way.
100%.
It was basically we wore out every test doer that was available at Goddard. But that's how
Right.
John and the rest of us learned how the properties behaved, how the detectors worked. So it really had to go on for quite a bit of time. And I agree that John could not write down exactly what he wanted because it hadn't been done before.
Right. And the nature of most NASA missions is you're trying to, I guess, predict and get control over things that are inherently uncertain that we're exploring.
Yeah.
Right.
Of course, most NASA missions are not done in-house, so we do actually have to write down much better what the requirements are so we can write a contract.
I don't think you could have done this at a house. I've told people that before.
Right.
Because they couldn't have written down what it is they wanted the contractor to do with a firm fixed price or a cost-plus type contract.
Right.
That would be very difficult.
And what was the strategy behind the in-house decision?
The strategy was two things. One, they all knew they couldn't send this out because they couldn't describe what it is they wanted. But number two, which was just as important, it was considered a training program for engineers. And now the chief engineer at NASA, Mike Riskevich, worked on COBE every day for 7 years. The director of engineering at Goddard worked on COBE every day. He's the one that built all the doors that we broke. The deputy associate...
Sure, he's glad you shared that with
I know.
Yeah.
The deputy associate administrator of NOAA, Abby Harper, worked on COBE every day. So it was a training program, and it was a best effort, and John could not possibly have written down what it is he wanted for a contractor to try to do.
Let me add also that because it was such a difficult mission, it was also attractive for engineers.
Yep.
When we wanted to recruit the very best people in the world to come work for NASA, we said, we have this almost impossible dream that we want to fulfill. How about you come and do it with us? And really brilliant people came to do this with us, and it was good recruiting.
The other thing is, in the last 2 years of this program, when it was hectic and people would come up and go, they're paying us to do this. They loved it. They just worked on it every day.
Right.
It's the best thing they could possibly do.
Passion, the excitement.
Yes.
Why don't we take a break maybe and see if there are any questions from our audience. We're at NASA headquarters. We have several people here, and so while people queue up, because we'll need to go to the microphone.
Norm Weinberg, I just had a question. If you couldn't write down your requirements, could you describe the process where you came to closure on your requirements?
Okay, that's a tricky question. In some ways, the requirements never quite closed. We did what we could. We said, this is what we can build. It better be good enough. We knew that what we had in mind was good enough to make some brilliant discoveries if nature was the way we thought. So we were able to back off on a number of things, but there were plenty of places where we didn't ever know if the requirement was the right requirement. We just had to wait and fly and see whether it would be so. So maybe I should comment on one particular thing. We didn't know how sensitive the microwave receivers needed to be to discover something. So there's a period of time when we were stalled and the budget wasn't available to do what we wanted to do. So during that time, new technology was coming available for those microwave receivers that said, well, let's cool them down to a lower temperature, they'll be more sensitive. We gained about a factor of 2 in sensitivity for doing that. It turned out that was just exactly what we needed to see what the universe had given us to see. We have very famous maps of the cosmic microwave radiation with pink and blue blobs on them. If the sensitivity had been a factor of 2 worse, we might not have seen those. So we were very fortunate, but nobody could have known when we started off the project how good we had to be. So we were lucky, but we made a world-famous discovery.
I would say, in regard to your question, and also the fact that when John did as much as he could do, and he described as much as he could possibly describe to us, the key was to have tested that satellite completely. And when it was completely tested, I remember telling John and the project we had done all we could do. So I think the closure was, it was completely tested. And I'll tell you another thing. Someone suggested, the chief scientist at NASA, suggested that when we were all done, we should put that satellite in a clean room at Goddard, in an RF clean room, in a clean room, and run it for 2 weeks. And just let it run on its own and let John and the scientists understand the idiosyncrasies of the gyros and the wheels and the noises. And that's how we brought it to closure. It tested it for 2 weeks, and we just changed the temperature of the room by plus or minus 10 degrees. It was in air. And just let it run for 2 weeks. And then we were done. So
you've mentioned, both of you have mentioned the testing being so vital. Is that, I mean, for any mission, any project, would you ever do a project where
well, I'll tell
not
you,
that,
and Frank Cebolino knows this. I mean, he and I used to tell people on Hubble, it was test, test, test. And this is not going to be done until we're done testing it. Now, an example on COBE is I deferred a test. Turns out it was on this instrument that won the Nobel Prize, John's instrument. I deferred a test because we had a schedule, and we tried, this thing arrived late. We put it in the door. We cooled it down for 6 weeks. We tried to test John's calibrator, and it didn't move. Typical Dewar failure rate. Took 6 weeks to cool it up. By then we had new harnesses and new things built. In fact, Mike Ruskevich, your chief engineer, worked on this every single day. So the key was we would defer a test, but we would never eliminate a test, ever. And I don't think Frank Cepolino would ever eliminate it. We would never do it.
Great. Question?
We have several such challenges at NASA today, yet we try to contract it out. Is it because of the lack of skilled workforce within NASA that we try to contract out?
Well, let me try. I mean, political questions at NASA. I think, John and I discussed this, the question I would be asked, could we do this? Could we do COBE now in the environment you're all in with much more oversight and independent technical authority? John and I think the answer is yes. The key is to find the people within NASA that want to do it and that can do it. And you would take the best people you would have. But the other thing we did on COBE, we found 3 of the best engineers at NASA, and we had them work on this program for 3 years, and they were the mentors to everyone that was on the program. So we had lots of young people. We had 3 superb mentors that watched over the whole program. And I'll speak for, I think you could do it again today. But you'd have, yes, the answer is you could do it again. I don't want to do it again.
Yeah, I think we could do it again. We clearly have much more capable technology now, so some things would be easier. This is a little bit like saying, well, I started off as a child and I walked to school barefoot in the snow, and it was uphill both directions. But we certainly have learned a lot. The technical tools that we have available are immensely more powerful. When I arrived at Goddard, our engineers were drawing our new observatory with pencils on big pieces of paper. And that's not what we do now. So some things are a lot easier and better, and that part surely we could do.
The only thing I would caution about all the new technology you have now, I would see young engineers now become enamored with analysis versus the analysis is great, but some of them just become enamored with it. In the end, you have to test it as well. So that if you had young people now, I'm sure they would analyze this completely. But they've got to remember they have to test hardware like this.
Right, so you have to run the analysis, but the testing gives you the experience, is what
Yes.
I'm hearing. The experience is the...
You cannot
is the
stand
critical.
up at the end of a program and say it's ready unless you've tested it. The analysis could be this high.
My question is related to testing. I want to go back to something you said at the beginning.
Next to you.
You said that you don't trust anything unless it's been tested. But how is that working for JWST in the case where you cannot test everything for that observatory?
Okay, I guess that's a question for me. Pretty clearly, we test what we can. And when a thing cannot be tested exactly as it will be operated in flight, then we must demonstrate to good satisfaction that we've done everything that we could do to learn about that particular part of the program. So for instance, we know that we can't deploy the full-scale sun shield for the James Webb Telescope in zero gravity and the right temperature. So what we have to do is to analyze what we can to test subscale versions, test them every possible way that we can test them so that we develop the experience. There are a few things we just have to say, I can't possibly test it exactly the right way, but I have to test every feature of it in some way so that we can be sure that we didn't just, forget something. So
the testing can be done in stages, and as John pointed out, you can use subsystems or small elements of a system and then infer by that testing that the full-scale thing should work. It's not the best thing you can do, but when it comes to JWST, it's the best they can do.
yeah.
Dennis and John, you talked a little bit about technology today, engineering experience, knowledge, dedication, all of those factors coming together. You can do it again. And I think you both made that point. But you didn't say anything about 7120.
We did.
With all of the bureaucracy now that 7120 imposes on you, how many hundred years you think it'll take for you to do the same thing today?
Glad you're getting the non-tough questions.
Since I don't work here anymore, I would say that what we did on COBE was, after the Challenger accident and we were going to launch on the shuttle, we went about our business the next morning. The next day, we started to look at every launch vehicle in the world, Ariane and Long March and Proton, and we just did it. The question is, would the system now have allowed us to have done all that? I think the system then and the system now, they want you to tell them what the solution is. They don't have solutions, anybody that's higher than we are. So I think in the end, we told them what we could do, and we basically told them how we were going to do it, and the system proceeded to let us do it. But I think the other thing is, I know you could become inundated with review teams and the paper, but I think the idea that we had 3 of the best engineers at NASA review this program, they were the ones that could stand up and calm a lot of committees down.
So if you have talent, that's your power.
The talent is the power, and I also think you need to tell them what you're going to do. If I go up above people and ask them what we should do, they're not going to know. I need to tell them what we can do. And the next day after Challenger, we proceeded to go off and try to find, and we found a solution.
Right. So it's owned by the team, and the team then drives how the system,
I realized 7120. I was involved with reviewing that and all, and it's a lot of it, to me, Seppi, is common sense in there. And if the system, and you have to push back on some of the people who don't know it's common sense, but some of that, I agree with it. It's common sense to do that work. And we did a lot of it, but it wasn't documented. So I would tend to push back on them and tell them this is how we're going to do it.
John?
I don't feel afraid of 7120. It codifies what ought to be done. And so if somebody in some other agency wants to know how to do big projects, I say, read our document. It's the Bible. And so I'm not afraid of it, but in a very innovative project, you certainly have to work it a little differently in different phases. At the beginning, you don't want the same depth of review that you want later when you're actually trying to prove that your real flight hardware is really going to work.
Right. Maybe this also leads to one of the, I was at Goddard from 1986 to 91.
Did you work on COBE?
I did not work. I'm the only one at Goddard who didn't work on COBE, I think. But I do remember speaking to John, and one of the things you said at the time was that the most important aspect of a mission is the people. The technology is important, the science is important, but it's the people. And can you talk to that a little bit, the importance of building the relationships, and how do you do that?
Certainly it's clear to me that the people are the ones that make the project happen. It's not an accident either when good people appear to work on a project. When people know that the project management's a good management and that their ideas are going to be respected and they're going to be respected, they'll want to work on the project. So people wanted to work on our project. And so we didn't have to go out and say, this is the great project. They heard from their friends that this was a great project. This was the thing to be on if you could be. And we were blessed with that, but I think people knew that the project was important. It had support from headquarters, it had support from center management, and we saw the same thing happening again with the new telescope, with the James Webb Telescope. When we said we were going to do this, and the administrator of NASA went to the Astronomical Society and said, we're going to do this, he got a standing ovation for doing that. So people knew that this was going to be a good project. So from everywhere, scientists and engineers came and said, well, I want to work on this project, how do I do this? So there's a kind of context that can be created which attracts the talent that you need.
I'll give you another example on COBE. After the shuttle accident, we basically put everybody on one big floor and we all worked together, engineers and scientists. It dawned on us after about a year, we hadn't had a staff meeting. The staff meetings were 16 hours a day in the hall. People were, the observatory manager, the instrument manager, John, it was just communication all the time. And we'd realized we didn't have meeting. It was just communication all the time. It was kind of interesting after we realized we hadn't had a staff meeting.
Right. So you attribute it to the, you talk about the sense that this was such an important mission that people just wanted to work there. So it's the power of that vision, of the dream.
Well, after the accident, and we came to NASA headquarters and we discussed that we could put this on a Delta, and we could do it, repackage everything. The Goddard Center director decided this would be the centerpiece for NASA and the centerpiece for Goddard, which we just loved the pressure.
Right.
But once it became the centerpiece, I mean, everybody wanted to work on it. The other thing is the last 18 months of a project, every one I've been on, the workers take over. They decide, we're going to finish this. And management will keep you informed. But the technicians and the engineers that are with the hardware every day, they decide they're going to finish it. And you just let them go. And you just help them every day remove obstacles.
And in terms of assembling the team, I mean, were you able to, how much input do you have in terms of who you get to work with in something like this? Do you have, because it's such an important mission, you're able to pick the folks you want? Or?
On an in-house program, as someone else alluded to the fact, they would like to give you young engineers because they want them to be trained. So we inherited Mike Bruskevich and other people along the way. But I think in the end, in any program I've been on, if it's the wrong person, the best thing to do is remove the person. And every person I removed on various programs, I would find them a job, but not this job. You need to go. And we replace them as we went. And you pick and choose as you go. You can't just put 30 people in a room and say, this is the team. You've got to watch them, and over time, some grow, some don't grow. As you and I pointed out, some can multitask and some can't. Well, you don't know that until you bring them on board. And the ones that can't do it, they have to go. But the ones that had to go, I would find them a job. It wasn't derogatory. This is the wrong person.
Getting the right person for the right position and being comfortable looking to do that.
Part of my job was personnel, was to find the right people.
Right. And in terms of the relationship, how did you work off of each other? Obviously, you have either you're very good at faking it, or you really care about each other, you respect each other. Was it as simple as John working the science and engineering aspects and Dennis working the management, or how did you work with each other?
The first example is John and I would meet every week in my office with the door shut, just to have lunch. We would have lunch, and we would just discuss the program, we would discuss people, it was communication. But we certainly, I mean, along the way, people would tell me, John never said this. But people higher than John said, Dennis, this is Nobel science. That's more pressure. And so we respected what John and the other principal investigators wanted to do. And our role was to understand them as much as anything. Periodically, I would ask John, what it was we were going to measure, because I was trying to understand. And John told me very interestingly one day, Dennis, I don't think about it. I have no preconceived idea of what it is I'm going to measure. Because if I did, the data, you could tend to skew what it is you're trying to measure. So I remember when I snuck up on him 2 or 3 times, John, tell me about the Big Bang. Nope, he wouldn't tell me.
So as the principal investigator, what is that role? What's that about? What were you trying to do?
Well, okay. First, I wanted to respond to something Dennis was talking about
Right.
in terms of regular lunch meetings. Well, for me, it was a real important part of the building of trust. If the investigators are not sure that the management's on their side, then they go nuts. But I sort of knew when I saw Dennis that if I had a concern or an issue, he would grin at me and twinkle his eyes, and I would say, okay, he's going to take care of it. It's going to be okay. And it was. So this happened enough that I could say, okay, scientists, I know you're worried about this, but the project management understands what the problem is, and they are on our side.
Yes.
And they are not going to fly it if it isn't going to work. That was the big issue. Are we going to fly something that hasn't been tested? And the answer was no.
No.
We're going to test it. But coming back to your question, what's the job of a PI like? Number one, I think it is to conceive the measurement that needs to be made, and then 2, translate that into some kind of engineering terms that a person really could build. So there were an awful lot of sort of trade studies that had to be organized by the principal investigators to say, well, okay, this is what I want to measure, this is what possibilities exist in engineering, what's the path that we're going to take through this to find a way. So, and eventually to translate the general desire into particular specific numerical things, like how big is the aperture, how sensitive are the detectors, what exact wavelengths are we going to use, how does that match up with the technology we can get. And so the principal investigator has a lot of responsibility and authority in this area. Now, in our particular case, as an in-house project, the principal investigators were not in charge of budget. That was something that the project management was better positioned to do. It would have been tricky for the PIs to do this, and we didn't have to. So that was the deal that we have. But we were on good terms, so it wasn't a problem. So, and then eventually the PI gets back the data, and with the science team that he's assembled, then tries to figure out what it means. So there's some wonderful surprises there, but pretty soon after launch, we knew right away that the equipment was working and we were going to get good stuff. So we did.
I think what I mentioned before, and John just said it again, he had no preconceived, he didn't have the solution that he was going to write the paper with.
Right.
He needed the data,
He was doing science.
doing
Yeah.
science.
Yeah. Let's open it up again to questions.
Well, I have a question that's it kind of follows on with some things you talked about earlier in terms of having requirements, not having requirements. Because we are in the political environment we are in, we do need to be able to articulate to those outside of the agency, at least on some grand scale, what we're trying to do. How do you, in this environment, and I don't know if, how familiar you are from a perspective of, but how would you be able to articulate non-requirements? I mean, if you don't know what your requirements are now, how do you go about trying to get funding, because it's the grand scheme of getting money to continue to do something that you don't know what the results are going to be? And how do you tell people outside of NASA that they should help us and support us in terms of money?
Well, I think that's a very great challenge. It is sort of the essence of the challenge of life, isn't it? How do you explain to the world why it is that what you want is a thing that we all should want? So if you were to ask me how should a principal investigator prepare for life, I'd say, number one, read and write. Study reading and writing and communication, because that's the essence of how we get to do what we want to do. We might think that science and engineering are the essence. Well, they're pretty important, but if you can't convince anybody that what you want to do is the right thing, then you're not going to get to do it. So there's a certain degree of persuasion that's required, and we have to say what we're after is really exciting, and even if we don't know what we're going to find, we know that it's really important, and this is why. So we didn't know whether the Big Bang was the right story, even. We said we have to go measure. We didn't know if the hot and cold spots would ever be measurable, but we knew that we had to go find out. So it is possible to explain this to people without having exact numbers. But then eventually it's the responsibility of coming up with real numbers and say this is what we are going to do. And at that level, then we have to persuade scientific and engineering review committees rather than the general public. Because I think the public trusts us as long as we have a good process. Not everybody knows that astronomers have something called a decadal survey. And every 10 years, the community of astronomers gets together with sponsorship from federal agencies to declare their intentions and their highest priorities. And so we're currently doing that right now. We'll find out what the rest of the world thinks we should do. So that's a process that gives a scientific blessing to the ideas of a few selected projects and enables us to communicate to the public.
You're able to build, through this inclusion with the scientific community, you get, in essence, your influence for priorities, and
Yeah.
that's a power base.
Yeah, and so even the Cosmic Background Explorer, the COBE, had to go through competitions. And we were reviewed, like every other project, against others and say, this is the best among several. And this is what the agency is going to do, and the scientific community is then convinced. So then we can say, okay, world, this is why we're doing this. It's not that hard, but you have to do it well.
Mm-hmm. I think the key is what John pointed out is communication. Writing it down and also communicating it.
Right. I know you spent a little bit of your career at headquarters. Did that give you any insight in terms of getting support from an agency level on the strategy at, I guess, a portfolio or program level? Or
I would say working down here for a year was enough. But I can tell you that after I had worked down here for a year, then I got involved. I was the deputy on Hubble, and then I went to Johns Hopkins University. Once I was here for a year, I understood what all these questions meant and what all this crisis meant and what these budget cycles were. It was helpful. I mean, it would have been helpful even before COBE to have worked down here. Okay. And then go to a field center and be involved on a program and understand the pressures that go on down here. It was helpful to work here for 1 year.
Not a year and a day.
No, that was enough.
Yeah, I think my question is for Dennis. To what extent did you see systems engineering contributions to the success of COBE? And then the second question I have is, over the years, and probably that's to John, scientists or PIs are coming close to refining requirements, at least to help the engineering teams, even though they have to have this kind of spectrum to dream around in terms of what they are looking out for.
System engineering, I totally agree with system engineering. If you don't have system engineering, you're just building subsystems and pieces, and you don't know what it is you put together. And I think what we did is, as I pointed out, we brought in the 3 best engineers we could find that did system engineering from a global perspective on COBE. One of them analyzed every electrical circuit on those instruments and on that spacecraft. One of them reviewed all the analysis mechanically and thermally on the entire program. And one reviewed the entire Delta launch vehicle. So the system engineering, it was end to end. It was the instruments, the spacecraft, and the launch vehicle. Now below that, there were systems engineers working on all of the instruments and the spacecraft subsystems, and they did their piece. But we brought in 3 people who had all the experience to look at the whole system. So we couldn't have done it unless we would not have been able to get up at the end and say this was done until those 3 system engineers said we didn't forget anything.
Okay, let me add a little bit about systems engineering, which is that the systems engineers that I worked with are the ones who are sort of closest to speaking as scientists to engineers. My systems engineering partners were the ones who knew how to take what I said and turn it into engineering terms. So I didn't have to do it all by myself. I thought I learned a little bit about systems engineering, but I know that I don't know nearly enough to be a real one. So you had another question, though. About requirements and how do we turn them into numbers nowadays? Well, these days we have a lot better ability to simulate things in computers before we build them. So nowadays we also can predict and simulate what the sky is like. So we can simulate the first stars and the first galaxies, and we have some idea of what we're looking for a lot better than we did 30 years ago. So that helps a lot too in trying to get to real numbers for requirements.
I would also say when John would, or any scientist on any program, comes up with what their requirements are, the engineers can sit down and work with them and have those requirements filtered down to each subsystem. They don't have to do it all on their own.
Let me also add that we end up always being driven by money. That the scientist says, I want this, and the budget people say, we can afford this. So the scientist has to say, well, okay, that is good enough for my problem, or not. And so if it is good enough, then that's what we build, because who wants to spend more money?
I'll give you an example. On John's instrument, on COBE, say 7 months before launch, something like that. Engineers love to find new things, and it's better than what we had. So somebody came in on a configuration control request to change a circuit on John's instrument. And my answer was no. First of all, we don't have 2 more weeks to do it. It wasn't the money as much, but to spend 2 more weeks to develop a better circuit for John's instrument, even though in the end it won the Nobel Prize. So I said no, and I actually got up and walked out of the room. But there was mumbling about what does he know? But the next day, so they all left. The next day, they came back with another idea they could do in 3 days. The idea was just to say no, and it contained the problem, and they put it back, and then they came back within 24 hours. Here's what we can do in 3 days, and it's better. And the answer then was yes. It's just iterations and trade-offs.
Your comment about budgeting was a great lead-in for my question. With a 100% failure rate at various moments, how do you keep your leadership focused on funding your project? And we deal with that a lot here with the budget constraints. So that leads me to that question.
Ask it again.
I said with a 100% failure rate, how do you keep your leadership focused on funding your project? Sorry, it's another political question.
No, it's okay. Well, let me say that, look at it, the perspective was the pieces that were failing were a small piece of an instrument. The rest of the program was on schedule. The spacecraft, the ground system, the launch vehicle. It was these small pieces that were affecting John's instrument and the other cryogenic instrument. Didn't mean the whole project was stopped. In fact, we would do things in parallel. Those things were tested in test doors, and we would find out they failed, and we would fix them along the way. But in the meantime, we can then go to management and say, spacecraft's on schedule, the ground system's on schedule, but these pieces ended up on the critical path technically and schedule-wise. So I think the system could deal with that.
I have a question about the training thing that you mentioned earlier, the training aspect of the program. I think there's some concern about the ability to do that today, given some tightness, running a little leaner, meaner. Are we doing the in-house projects that give us the space and the time to say we can include some extra engineers, we can train them, we can play around a little bit, so that in 5-10 years we'll have another crop of excellent engineers leading our agency, as you mentioned had happened from COBE.
Let me give you a primary example. I was asked to come to Goddard recently and review the MMS program, this big four big satellites, blah, blah. It's all in-house, it's all young engineers, and it looked like deja vu. The other thing was, so I think that the system at Goddard, and I think the director of engineering, the person that built all these doers we broke, Orlando Figueroa, he understands this. He understands he needs to train those engineers on the in-house program. The other thing is the Goddard Center director recently asked me and Orlando, how did we do it on COBE? And versus how could we do it similar to that now? So he's aware of the fact that what we did worked. We trained all these people, and we built this Nobel science. And I think MMS at Goddard is the primary example that they're doing it again. But I think the reason is, possibly, is that the director of engineering is there, the chief engineer at NASA is here, and they were involved with COBE. So they understand what you have to do now. I think they understand it. There's no other way you're going to grow people to do this unless you let them do it on an in-house program that I know of.
There's another question.
Yes, you both seem to indicate previously that you had the fortunate experience to work on a really good team. I'd be curious, in your experience, what contributes to some project teams failing?
Well, I can't tell you where I was. I got involved with a program that a third of this group had to go. They were the wrong people. It was the wrong mix of people. And as I pointed out to Ed, I was the project manager somewhere on a program, and it was all dysfunctional. It was a completely very dysfunctional group. And one by one, people had to leave until we brought in the people that were functional and could work together. I think you can have a program, as I mentioned before, you bring people in, you put them on a program, and you could realize they're not playing well together. Then somebody has to go, one by one. And I didn't mind, because my job was to find the right people to do each job.
John, any thoughts on why do projects fail?
Well, I don't have independent thoughts on this subject because I don't have many projects to draw from, but I would say Charlie Pellerin's book on how NASA builds teams is a good textbook on what can work well and what doesn't work well and what you might do about it. So he was at headquarters when we launched the COBE, and he wanted to make sure that we did it well. There were times, I think, when he was very urgent to us to do it differently, but he also wanted to make sure that we did it right. So that's, I don't know, I can't really explain, but there is a certain magic of doing it well, and you can tell when it's not happening.
And I think the key is you've got to be able to tell when it's not happening, and you've got to act and change it. Just don't let it go on like that. Certain people, and it'll become obvious who's dysfunctional and who doesn't match. It's the wrong mix of people. When you find that out, you need to act and change it.
So it's about the people, it's about defining reality, and it's about being able to adapt. And perhaps we go into that segment. Obviously one of the fascinating, difficult parts of the story of COBE was 1986, we have the Challenger loss. And talk to me about innovation and adaptability, and that was a threat to COBE as a mission.
Let me speak for John, because John said this to me recently. The day after the Challenger accident, as horrible as it was, we came to work at Goddard, and we were going to find a solution to this problem. We were not going to launch a shuttle from California in a polar orbit for COBE ever, as far as I was concerned. John's comment recently was, we didn't know we couldn't do this. So we went about it and found a solution. My opinion was, everyone above me, we were all wringing our hands in a terrible position NASA was in. My position was, and my job was to find a solution. So we went about it, and we spent 6 months looking at every launch vehicle in the world, from Ariane Space. I met with Ariane Space in Washington 3 times. In the end, I got in trouble because NASA didn't want me to. But my job was to find a solution, and after a few months, we had a solution.
We go to John. Originally, why was COBE slated for the shuttle, and what was the thinking there, and then how did you start thinking about the transition?
Okay, well, maybe I should say that in 1974, when NASA asked for proposals, they offered the Delta rocket as the launch vehicle.
Oh, okay.
And so that's what we did propose. And when I came to Goddard in Greenbelt in '76, that's what we studied for quite a few months. And then it wasn't too long after that NASA and Congress and whoever was involved in the decision process said, well, okay, well, we're just not going to have any more Deltas because we're going to decide to put all our eggs in the shuttle basket. And that was a very strange process, which I don't understand. I just was standing at the side wondering about the strange behavior of groups. Anyway, that was the deal. So none of us liked it, but okay, that's the command. We will do it. And we were told not to complain. So we did find a way. Just as Dennis said, we'll find a way. Well, we found a way to put the thing that was supposed to be on a Delta onto the shuttle. But it did require the West Coast shuttle, which was in the plan at that time. And then it never ever was launched from the West Coast. So that was the plan.
I think the bottom line is, it was up to us to find solutions.
come up with ways to make it work. And how did you deal with the, the issue of you have this strong vision, this dream that people are, you obviously have energy going into a direction. Did you have any concern that at any point that this isn't going to happen, or?
My opinion was the day after the accident, it was far better for us to go about our business and find solutions than to sit there and feel as bad as we felt. I mean, might have cried the night before. The next day, it was we are going to find a way to finish this program. And we focused on it from the day afterwards, and I think that's the best thing we could have done for the people, too. Right. They were focused.
Yeah, I felt that, too. I never doubted that we would find a way, because I knew we had a Delta plan originally, and I knew that we had thousands of pounds of extra weight on the mission design that we had that was just specific for the shuttle. So I thought, well, maybe there is a technical solution. And I didn't know how different it would be. We turned out to be pretty lucky about it because we didn't have to redesign the instruments because they were just about finished. We had to redesign the mechanical structure and change the propulsion system. But after that was done, we came pretty darn close to what the capability of the big Delta could be. And it was pretty close. It was a struggle, but our team carried it off.
In your story, it seemed, I mean, when a lot of people think of missions, NASA missions or projects, there's this sense of there's a plan and there's a schedule and there's an implementation and there's a discipline and a process, which obviously is there, but you also bring in a lot of the creativity, the need to adapt, and the innovation. I mean, any thoughts in terms of, which is more common? Is it a straight kind of a path of implementation, or is it a struggle or a constant innovation and adaptability of dealing with these forces?
Someone asked this question about John coming up with requirements and then going through the process and budget requirements and NASA headquarters. But for this type of program, for this type of science, I think the system understood this has never been done before. And John can tell us just so much what his requirement is. And then the system, we needed to come up with solutions. And then in the middle of that, we had a 100% failure rate, but maybe certain pieces failed, but the rest of the system kept progressing. But then there was the accident, and then we had to start all over again. But I think the system, when I would come down here and explain all this, the system understood what we were doing. I think the key was we explained to them what it was we were doing. We didn't come down here and wring our hands and say, we don't know what to do, because if we don't know what to do, I'm not sure anybody, here knows what to do. We need to help them figure it out. So we came down and told them what we were going to do. And if it's reasonable, the system, I still think the system allows you to do well.
I wanted to add also that the COBE was not a traditional astronomy project. NASA was used to doing astronomy projects. It was not used to doing one of these. This is not a telescope you can point at anything. This is a survey of the whole sky. There are no guest investigators making proposals the way we have for Hubble or for the IUE that came before. So this was all different, and there was a pretty substantial group of scientists out there who didn't think this was worth the bother. But we had a program scientist at headquarters who really did understand. That was Nancy Bogus, and so she actually put her shoulder behind it and made sure that everyone knew why we had to do this. And she was a real reason for the existence of a lot of infrared observatories. The FIRAS satellite that came early, came before COBE, then the Spitzer Space Telescope and the COBE and even SOFIA. All of these things were hatched while she was able to push. So we had the blessing of a person who really understood and could explain to the world why these were so important, regardless of particular digits and numbers here and there in a requirements document. At the top level, people knew this was really important. And
yeah, you had the support of the community. One of the things I'd mentioned to Dennis, going back, it's probably about 20 years ago, you were talking at it's probably a Goddard leadership course. And I remember you got a question from someone in the audience about how do you deal with the difficulties of just working in the system, whatever the system is. And I always remembered something you said, that the system is chicken. And I interpret that to mean that what a leader has to do is, you know what your responsibilities are. You don't use excuses that there's something out there that stops you. You figure it out. I mean,
as Frank Sepulveda put it, I could come back in here now and tell you 7120, I can't get this done. But I gave a talk recently with somewhere in Annapolis with you people, and I said, just tell me what it is. What is the current situation at NASA? Is it 7120 or what is it? And I'll work around it or I'll work with it. But I just need to know what it is. I mean, you can impose TQM or whatever it is. We can work that out. You can work with it. And when I say that the system's chicken, the system needs me to tell them what we can do.
Right. It's leadership.
Leadership.
Thoughts?
Yeah, I would say the same. Another way of saying it is that there's a world moves for a person who knows what he wants. And so we say, this is what we need, this is what it takes. And people do want us to get the job done. They don't want to say, well, we just spent all this money and it's not going to work. They want us to get the job done. So please tell us what it is.
After the accident, I came down and met with Arianespace in Washington. I didn't ask permission. My job was to find solutions. And if it's a French rocket, whatever it is, then I'll come back to John when I remember coming back. And we could work these, but I had to have solutions. Leadership.
You've also both talked about the importance of mentors for people working. Who are some of the people that you learned from, that you respected, your mentors? John?
Okay, well, pretty clearly I learned an awful lot from my thesis advisor in Berkeley. Then Pat Thaddeus was my mentor as a postdoc in New York at the Goddard Institute for Space Studies. Then I came to Goddard, and Mike Hauser was my mentor. All of these people, not that much older than I am, but enough that they knew something I didn't know. And they also all said, well, here it is, you do this. So it wasn't so much that they told me how to do it, but they said, here's this job, this is really important, and it's yours. And so then I would come back to them and say, I don't know what to do now, let's talk. But it's not like instruction in how. It's more, this is important, let's talk together and make it happen.
I would say that when I was a working engineer, there were many project managers, as I mentioned. Some would empower people, some would try to do it themselves, some would be listeners, some would remove obstacles. But I watched each one of them and learned from each one of them. The second thing is that there were certain people above me at NASA who would call me periodically and say, how are you doing in the middle of this project? And I would proceed to tell them, you want to know how I'm doing? And they would let me talk for 10 or 15 minutes. And that's all they did. And then they would go back to work and I would go back to work. But there was always someone that I wouldn't go up there and wring my hands and tell them I don't know what to do. But at least there were people above me that would listen. And that made a big difference versus me versus the whole system.
So if both of you were advising people who are starting their career, whether it's engineering or management or science, what tips would you give in terms of how to go about it? Or what's the, if we can get it down to
I'll give you the biggest tip of all is to be a listener. You are not going to learn when you're talking. And I think as an engineer, sit in meetings, go to meetings, sit on projects, but watch and listen, and you'll learn it all.
John?
I'd say that's awfully good advice. Another part, if you're the scientist and you're wondering where to go, so something will turn out well, go where the action is. You can sort of tell what's happening in the world and what the excitement's about. So if you choose to go there, maybe you have a chance to get noticed and to contribute and eventually to be able to lead something. So I wasn't actually that good at this, but it turned out I was lucky. Because, I worked on the cosmic background radiation as a graduate student. It turned out to be really, really, really important. Mm-hmm. Then I chickened out for a while and I got drawn back into it. So anyway, I went where the action was. And then when I got a call, would I like to work on the new James Webb Space Telescope, which wasn't called that yet? Yeah, sure, that's where the action is. So I'm having a good time by going there. And when you go there, there's a lot happening, and good people to work with, people to learn from, anyway, so that's part of it. I already mentioned, I think, reading and writing are really important too, and a lot of our people don't appreciate how critically important that is. When I finished my thesis project, it was hard work to write. I thought, I'm so glad I don't have to write anything anymore. And I spent the rest of my life writing. So I didn't expect it, but it's really important.
And I actually remember the day we launched COBE, there was a press conference, and all I said was it was a joyful ride. After 7 years of turmoil, and you can enjoy this work. If you enjoy the people and you decide you're going to try to solve these problems yourself.
I would have said almost exactly the same words as Dennis was describing his thoughts. I thought, I would have said that, I would have said that, I would have said that, because I feel also the sort of personal satisfaction of solving problems and of working with great people. If I didn't like the people I was working with, it wouldn't be fun. But I do. I enjoy them, and I think we all enjoy each other.
Yes.
You know, the project I'm on now, when we have a staff meeting, you can hear people laughing, and down the hall, people hear us laughing, and they say, "Can I get on that project?" So, you know, it's possible that this high-stress environment is actually good for us in a curious kind of way. But it takes a good sense of humor and a sense of sort of faith and trust that this is the right place to be and that the system is working with us. As long as we know that we have the backing of our management and of the general public, then it's fun. I think it would be scary if we didn't think that, but we do have it. And so we are entrusted, entitled to spend the public funds for the most amazing projects that we could imagine, and to put people into space, to discover the beginning of the universe. And I can't imagine something that would be more fun than that. So that's why I'm here.
Well, this has been a lot of fun for me. It's gone very fast. Many more questions, but we only kind of tipped it. But I think who you are and the team, obviously, in terms of COBE and the Webb Space Telescope, speaks a lot. And so this has been wonderful. I want to thank the audience we have here for joining us and asking the questions. I want to thank the NASA TV folks for doing what they do to make this work. And particularly, we would like to thank one more time John Mather and Dennis McCarthy for this wonderful story and time together. So thank you very much.
Thank you.
Thank you, John.
Hey, that was fun.
It was.